There's something out there, something so large that calling it large doesn't really capture what it is. We've given it a name. We've measured it. We've marked where it sits in the sky. And still, when you sit with the idea of it long enough, you start to realize we don't actually know what we're looking at. This isn't a mystery in the usual sense. It's not hidden. It's not invisible. We can see it. We've detected it. But seeing something and understanding what it is are very different things. And this thing might be the largest structure we've ever found in the universe. Let's start with something familiar. Imagine standing outside at night. You look up. The stars seem scattered, random perhaps, like salt spilled across black cloth. That's how humans saw the sky for most of our history. Random points of light. Beautiful, but random. Only they're not random. If you watch long enough, if you pay attention across seasons and years, patterns emerge. The stars move together. They form groups. Neighborhoods in a way. Our sun belongs to one of these neighborhoods. We call it the Milky Way. And for a very long time, we thought the Milky Way was everything, the entire universe, all of it. Then we realized we were wrong. The Milky Way is just one galaxy amongst billions, perhaps trillions, each containing billions of stars, each star potentially circled by planets. The scale expanded so quickly that our words struggled to keep up. But even that wasn't the whole picture. Because galaxies aren't scattered randomly either. They gather, not because they want to, not through any intention, but because of gravity. That familiar force that keeps your feet on the ground, that pulls an apple from a tree, that same force reaches across empty space and draws galaxies towards one another. So galaxies form groups, small clusters at first, a few dozen galaxies orbiting each other slowly, like an extremely slow dance that takes billions of years to complete. Then those clusters gather into larger structures, superclusters, thousands of galaxies, tens of thousands, all connected by invisible threads of gravity, all drifting together through space. And this is where our intuition starts to fail. Because when we map these superclusters, when we step back far enough to see the whole picture, the universe doesn't look like we expected. It looks like a web, or perhaps a foam. Galaxies aren't spread evenly through space. They're clustered along filaments, long chains of matter stretching across hundreds of millions of light years. Between these filaments lie voids, enormous empty regions where almost nothing exists. The universe has structure, large-scale structure, and we're still working out why. But there's something else, something that appeared in our observations that doesn't quite fit the pattern, something too big. Imagine looking at a map of a city from above. You see streets, blocks, neighborhoods. Everything has a scale that makes sense. Houses are a certain size. Blocks are larger. Neighborhoods larger still. But then you notice something. A building that's not the size of a house or even a block. It's the size of an entire district. So large that it breaks the pattern. It makes you wonder if you're reading the map correctly. That's what we found in the universe. A structure so large that it challenges what we thought we understood about how structures can form. We call it the Hercules Corona Borealis Great Wall. But that name doesn't really help. It's just a label we've placed on something we don't fully comprehend. It's not a wall in any physical sense. It's not solid. It's not made of anything you could touch. It's a concentration of gamma-ray bursts, signals from the depths of massive stars. Explosions so powerful we can detect them from billions of light years away. And these bursts aren't spread evenly across the sky. They cluster. In one region of space, across a stretch so vast that light takes 10 billion years to cross it, we see more of these bursts than we should. 10 billion light years. Let's stop there for a moment. A light year is the distance light travels in 1 year. Light moves faster than anything we know, faster than anything with mass can move. It crosses the distance from Earth to the Moon in about 1 second. In 1 year, light travels nearly 6 trillion miles. This structure is 10 billion of those years across. Our entire galaxy, with all its billions of stars, is only about 100,000 light-years wide. This structure is 100,000 times larger than that. But size alone isn't what makes this strange. The universe is big. We expect big things. What makes this structure unusual is that it exists at all. According to our models, according to the physics we think we understand, structures this large shouldn't be able to form. The universe is expanding. It's been expanding since the beginning. And that expansion works against gravity. It pulls things apart. The farther away two objects are, the faster space itself stretches between them. For a structure to form, gravity has to win against that expansion. Matter has to clump together faster than space can pull it apart, and there's a limit to how large something can get. At least we thought there was. We have this idea in cosmology, a kind of cosmic speed limit for how large structures can grow. It comes from thinking about time, about how long the universe has existed. The universe isn't infinitely old, it has an age, roughly 14 billion years. That means there's only been 14 billion years for anything to form. Gravity works quickly on small scales. It can pull together a star in a few million years, a galaxy in a few 100 million. But the larger the structure, the longer it takes. And 10 billion light-years is really, really large. So when we found this concentration of gamma-ray bursts, when we measured its size, something didn't add up. There hasn't been enough time. Not enough time for gravity to gather that much matter across that much space into something we could call a structure. It's like finding a building that's taller than the time it would take to build it. Like discovering a tree that's older than the forest it grows in. The mathematics doesn't work. But the observations are clear. The gamma-ray bursts are there. They cluster in this region. We've checked the data. We've run the numbers. Different teams, different telescopes, different methods. They all see the same thing. So we have a choice. Either our observations are somehow wrong, we're seeing a pattern that doesn't really exist, a coincidence, a trick of perspective, or our understanding is incomplete. And this is where things start to feel uncertain, because we don't know which it is. We have theories, we have ideas, but we don't have answers, not definitive ones. Not the sort you can point to and say, this is what's happening. We're standing in front of something enormous, and we're not entirely sure what we're looking at. Let's think about what a gamma-ray burst actually is. When a massive star dies, really dies, it doesn't simply fade away. It collapses. All that matter, all that mass that's been burning for millions of years, suddenly has nothing left to burn. The forces that held the star up against its own gravity disappear, and it falls inward. In seconds, the core of a star compresses to something unimaginably dense. The outer layers bounce off this core and explode outward. We call it a supernova, one of the brightest events in the universe. But sometimes, in the most massive stars, something else happens. The collapse continues. It doesn't stop. It forms something so dense that it tears a hole in space itself. And in that moment, in the final instant of the star's existence, it releases more energy than our sun will produce in its entire lifetime. That energy comes out as gamma rays, the highest energy light that exists. These bursts are brief. They last seconds, sometimes less. A flash of the most intense radiation in the universe, and then it's gone. But we can detect them. Even from billions of light-years away, even from the far edges of the observable universe, our telescopes can catch that flash. And when we map where these bursts come from, when we plot their positions in the sky, most of them seem scattered, spread out, No obvious pattern, except in one region. In the direction of the constellations Hercules and Corona Borealis, we see more of them. Not a few more, significantly more. Enough that it's difficult to explain as random chance. If you flip a coin 10 times and get heads 7 times, you might think, well, that's just luck. But if you flip it 1,000 times and get heads 700 times, you start to suspect the coin isn't fair. That's what we're seeing here. Too many gamma ray bursts in one region of space for it to be an accident. So the question becomes why? Why would massive stars be dying more often in this particular region? Why would there be a concentration of these events across such an enormous volume of space? One possibility is that there's more matter there, more galaxies, more stars, more opportunities for massive stars to form and die. In other words, a structure, a real physical concentration of mass. But that brings us back to the problem. A structure that large shouldn't exist, unless we're wrong about something fundamental. Perhaps the universe is older than we think. Perhaps there's more time than we calculated for these structures to form. But we're fairly confident about the age of the universe. Multiple independent methods give us the same answer. 14 billion years, give or take a few hundred million. Perhaps gravity works differently on these scales. Perhaps there's something about the way matter clumps together that we haven't accounted for. That's possible. We know our understanding isn't complete. There are things about gravity we don't fully grasp. Dark matter, dark energy, the way space itself behaves on the largest scales. But changing our understanding of gravity is a big step. It's not something we do lightly. Or perhaps this isn't a structure at all. Perhaps we're seeing a pattern where none exists. Perhaps it's a statistical fluke. A random clustering that happened to occur in one region of space and not others. The universe is large. Really large. Large enough that unlikely things become inevitable somewhere. If you have enough space, enough opportunities, even rare events will happen. This could be one of those events. But here's the thing. We've run the statistics. We've calculated the probability of this clustering happening by chance. And it's low. Very low. Not impossible, but unlikely enough that it makes us uncomfortable. It's the sort of number that makes scientists pause and say, something's going on here. But we don't know what. And that uncertainty sits at the center of this whole thing. We have observations that suggest something enormous. We have theories that say it shouldn't exist. And we have no clear way to resolve the contradiction. So we're left with mystery. Not the dramatic sort, not the kind with a hidden answer waiting to be revealed, but the quiet kind, the kind where you realize your tools might not be good enough, that your brain might not be built to understand this, that the universe might be stranger than you thought. Let's talk about scale again, because even though we've said this structure is 10 billion light years across, I'm not sure that means anything to us. Not really. Our brains didn't evolve to think about distances like that. We evolved to think about the distance from one tree to another, from our home to the next village, from the ground to the sky. Even when we try to stretch our imagination, we hit limits rather quickly. Think about a mile. You can walk a mile in about 20 minutes. You know what a mile feels like. 1,000 miles is a long distance. That's driving across several counties. That's a journey that takes most of a day. The Earth is about 8,000 miles across. That's already difficult to picture. You can fly around it, but you can't see it all at once. Not from the ground. The Moon is about 240,000 miles away. That's 30 times the width of Earth. We've sent people there. It takes a few days in a rocket. The Sun is 93 million miles away. That's nearly 400 times farther than the Moon. Light from the Sun takes about 8 minutes to reach us. And already we're losing our grip on what these numbers mean. 93 million miles doesn't feel like anything. It's just words. But let's keep going. The nearest star beyond our Sun is about 4 light-years away. That's 25 trillion miles, more than 200,000 times the distance to the Sun. If you could travel at the speed of the fastest spacecraft we've ever built, it would take you 70,000 years to get there. 70,000 years. That's longer than recorded human history. And that's just to the nearest star. Our galaxy contains hundreds of billions of stars. They're spread across 100,000 light-years. The distance from one side of the galaxy to the other is so vast that if you could somehow travel at the speed of light, it would take you 100,000 years to cross it. But you can't travel at the speed of light. Nothing with mass can. So that journey would take even longer, much longer. The next galaxy, the closest large galaxy to ours, is about 2.5 million light-years away. The light we see from it tonight left that galaxy 2.5 million years ago, before humans existed, before our ancestors came down from the trees. That's how long it takes for light to cross the empty space between galaxies. And galaxies are everywhere. In every direction we look, as far as we can see, there are galaxies. Billions of them. Each containing billions of stars. Each separated from the others by millions of light-years of mostly empty space. When we map all these galaxies, when we chart their positions and try to understand how they're distributed, we see that cosmic web again. Filaments of galaxies stretching across hundreds of millions of light-years. Clusters where thousands of galaxies gather. Voids where almost nothing exists. The largest structures we know of, the ones we understand, the ones that fit our models, are about 1 billion light-years across. That's already incomprehensibly large. That's already pushing the limits of what we think can form in the time the universe has existed. But this thing, this Hercules Corona Borealis Great Wall, it's 10 times larger than that. And somewhere in trying to comprehend that scale, something breaks. Not in the universe, in us. Our ability to picture it fails. The numbers become meaningless. We can say 10 billion light-years, but we can't really hold that idea in our minds. It's too big, too far beyond anything we have experience with. And perhaps that's part of the mystery. Perhaps part of why we don't know what this structure is comes from the simple fact that we're not built to understand things this large. Our tools can measure it. Our telescopes can detect it. Our mathematics can describe it. But we can't really grasp it. Not in the way we grasp the size of a building, or a mountain, or even the Earth. There's a moment that happens when you look at something truly large. Not just big. Truly large. Your mind tries to take it in. Tries to fit it into categories you already understand. Tries to compare it to things you know. And for a while that works. This building is taller than that one. This mountain is bigger than the hills around it. This ocean is wider than any lake. But at some point the comparisons stop working. You run out of things to compare it to, and you're left with just the thing itself. Enormous. Incomprehensible. Beyond scale. That's what happens when you try to think about the largest structures in the universe. You can't compare them to anything human-sized, or even planet-sized, or star-sized. You can only compare them to other cosmic structures, and even then the numbers become abstract. Saying something is 100,000 times the size of our galaxy doesn't create a picture in your mind. It just creates a sense of bigness, of something beyond understanding. And that brings us to a strange place, because we're trying to understand what this structure is. We're trying to work out if it's real, if it's a coincidence, if it's something our theories predict, or something that breaks them. But we're doing all of this with brains that can't really comprehend the scale we're dealing with. We're using intuition built from human experience to make sense of something that exists on a scale where human experience means nothing. So when we say we don't know what it is, part of that is about physics, about the limits of our models and our mathematics. But part of it is about us, about the limits of what a human mind can hold. Let's think about time for a moment, because distance and time are connected in strange ways when we talk about the universe. When we look at this structure, when we observe these gamma-ray bursts, we're not seeing them as they are now, we're seeing them as they were. Light takes time to travel. That's not usually something we notice in daily life. When you turn on a lamp, the light seems to appear instantly. But it doesn't. It takes time. Just an incredibly small amount of time. Too small to notice. But across cosmic distances, that travel time becomes significant. When we look at the sun, we see it as it was 8 minutes ago. That's how long it takes light to cross the space between the sun and Earth. When we look at the nearest stars, we see them as they were years ago. The light left those stars years before it reached our telescopes. When we look at other galaxies, we see them as they were millions of years ago. Tens of millions. Hundreds of millions. The farther we look, the further back in time we see. And this structure, these gamma-ray bursts, are coming from billions of light years away. 10 billion light years away. That means we're seeing them as they were 10 billion years ago. The stars that created these bursts died 10 billion years ago, long before Earth existed, long before our sun formed, long before anything in our solar system existed. We're watching ancient history, events that happened when the universe was less than a third of its current age. And that adds another layer to the mystery, because we're not just asking, what is this structure now? We're asking, what was this structure 10 billion years ago? And we don't know what it is now. We can't see it now. The light from now hasn't reached us yet. It won't reach us for 10 billion years. By the time that light gets here, if anyone is around to see it, the universe will be 3 times older than it is today. So we're working with old information. Very old information. We're trying to understand something based on snapshots from when the universe was young, from when things were different, when the structure of space itself was different, and we're using that old information to make guesses about what might be there, what might have been there, what the universe was doing back then. It's rather like trying to understand what a person is like by looking at a photograph of them as a child. You can see some things, you can make some guesses, but you don't really know who they became, what they look like now, what they're doing. The photograph is evidence that they existed, but it's not the full story. That's what these gamma-ray bursts are. Evidence that something existed, something large, something unusual, but not the full story. We have other large structures we can look at, structures we understand better, structures that fit our models. The largest of these are the filaments in the cosmic web, long chains of galaxies stretching across hundreds of millions of light years. These filaments formed because matter in the early universe wasn't perfectly smooth. There were tiny variations in density. Some regions had slightly more matter than others, and gravity amplified those variations. The denser regions pulled in more matter. They grew denser still. Over billions of years, matter flowed along invisible paths, gathering into streams, forming the filaments we see today. This process we understand. It matches our simulations. When we model the universe on computers, when we let gravity work on billions of particles over billions of years, we get structures like this: filaments, clusters, voids. The cosmic web emerges naturally from the physics, but there's a limit to how large these structures can get. The limit comes from time, from the age of the universe, from how fast gravity can work. In 14 billion years, gravity can only pull matter together across a certain distance. Beyond that distance, the expansion of the universe wins. Space stretches faster than gravity can pull. We can calculate this limit. It's not precise, but it's somewhere around 1 billion light years. Perhaps a bit more, perhaps a bit less. It depends on the details. But 10 billion light years is way beyond that limit, 10 times beyond it. So either our calculation is wrong, or this structure formed differently, or it's not really a structure at all. The idea that it's not really a structure is worth sitting with, because what we're seeing is a clustering of gamma ray bursts, signals, events, not the matter itself. We're inferring that there's matter there because that's where the bursts are coming from. But we haven't directly measured the matter. We haven't mapped the galaxies in that region. Not completely. So perhaps the clustering is real, but it doesn't mean what we think it means. Imagine you're looking at a map of where lightning strikes occur, and you notice that lightning strikes cluster in certain regions. More strikes here than there. You might assume there's something about those regions that causes more lightning. Higher ground perhaps, more water, more storms, and usually you'd be right. But sometimes the clustering is just chance. Sometimes in a random system, you get clusters, areas where events happen to occur close together, not because of any underlying pattern, but just because randomness isn't perfectly uniform. Random doesn't mean evenly spread, it means unpredictable. And unpredictable things sometimes cluster. Could that be what we're seeing? A random clustering of gamma ray bursts that looks like a structure but isn't. Perhaps. The probability is low. But low probability events happen, especially when you have a large enough sample size. And the universe is a very large sample. But that explanation feels unsatisfying, not because it's wrong, we don't know if it's wrong, but because it requires us to accept that we got unlucky, that we happened to find the one region in the observable universe where random chance created something that looks like a violation of physics. And scientists don't particularly like that, not because they're stubborn, but because science works by assuming that what we observe has a cause, a reason, a mechanism. Saying it's just random is giving up on finding that mechanism, so we keep looking for other explanations. One idea is that the universe isn't as uniform as we thought. When we model how structures form, we assume that matter was spread almost evenly in the early universe. Small variations, yes, but nothing dramatic. Nothing that would create enormous differences in density. But perhaps that assumption is wrong. Perhaps the early universe had larger variations than we thought. Perhaps there were regions with significantly more matter, regions that could form structures faster, larger structures, structures that violate the limits we calculated. If that's true, it would change our understanding of how the universe began, how it evolved, how structures formed everywhere, not just in this one region. It would be a significant change, but it's possible. Another idea involves dark matter. We know that most of the matter in the universe isn't the sort we can see. It doesn't emit light. It doesn't interact with light. We call it dark matter because it's invisible. We only know it exists because of its gravity. Galaxies rotate faster than they should based on the visible matter we can see. Something invisible is adding mass, adding gravity, holding things together that should fly apart. That something is dark matter, and it's everywhere, in every galaxy, around every cluster, along every filament. There's more dark matter than visible matter, about 5 times more. So when we talk about structure formation, we're really talking about dark matter. That's what provides most of the gravity. That's what pulls things together. But we don't fully understand dark matter. We don't know what it's made of. We don't know exactly how it behaves. We can measure its effects, but we can't see it directly. So perhaps there's something about dark matter that we're missing. Perhaps it can form structures in ways we haven't predicted. Perhaps under certain conditions, in certain regions, it behaves differently. Perhaps this enormous structure is a sign of that difference. Or perhaps it's something else entirely. Perhaps there's a process we haven't thought of, a mechanism we haven't discovered, a piece of physics we don't know yet. The universe has surprised us before. We thought galaxies were the largest things that existed. Then we found clusters, then superclusters, then the cosmic web. Each discovery pushed our understanding further, forced us to update our models, made us realize the universe was more complex than we thought. Perhaps this is another one of those moments. But the uncertainty remains. We can speculate, we can propose ideas, we can run simulations and make predictions. But we don't know. Not yet. Perhaps not ever. There's a humility that comes with that. A recognition that the universe is under no obligation to make sense to us, that our understanding is limited, that there are things beyond our current ability to comprehend. And perhaps that's all right. We've been looking at the sky for thousands of years. For most of that time, we didn't understand what we were seeing. We made up stories, gods and heroes, patterns and myths. Then we started measuring, tracking the movements of stars and planets, finding regularities, discovering laws. We learned that the Earth isn't the center of everything, that the Sun is just one star amongst many, that our galaxy is just one galaxy amongst billions. Each realization made us smaller, but also more aware, more conscious of our place in something vast. And now we're looking at something so large that it challenges the very framework we've built to understand the cosmos. We're not even sure if it's real in the way we think about real, if it's a physical structure or a statistical artifact, if it's telling us something profound about the universe or just showing us the limits of our observations. We don't know, and perhaps that feeling, that uncertainty, is part of the point, because it reminds us that we're still exploring, still discovering, still at the beginning of understanding. The universe is old, 14 billion years old. Human civilization is a few thousand years old. Modern science is a few hundred years old. Our ability to observe the deep universe, to see these distant structures, is less than a century old. We're newcomers. We've barely started looking. And what we've found so far is that the universe is larger than we imagined, more complex, more strange, full of things that don't quite make sense, that push against our theories, that force us to question what we think we know. This structure is one of those things, a collection of signals from the early universe, a clustering of explosions from dying stars, a pattern in the sky that might be the largest thing that exists, or might be nothing at all. We'll keep observing, keep measuring, keep trying to understand. New telescopes will come online, better instruments, more sensitive detectors. We'll map more of the sky, find more gamma-ray bursts, see if the pattern holds, see if it grows clearer or fades into randomness. We'll run more simulations, test more models, try to work out if something this large can form, if it fits with what we know, if it requires new physics, and gradually, over years or decades, we'll narrow down the possibilities. Perhaps we'll confirm that it's real, a true structure, the largest thing in the universe. Perhaps we'll determine that it's a fluke, a statistical anomaly, nothing special. Or perhaps we'll find something in between, something we didn't expect, something that opens up new questions. But for now, we're in the uncertain space, the space between observation and understanding, the space where we know we've seen something but don't know what it means. And there's something peaceful about that, about sitting with the mystery instead of rushing to solve it, about accepting that some things take time to understand, that some things might always remain partly unknowable. When you look up at the night sky, you're looking at light that's been traveling for years, for millions of years, for billions of years. You're looking at the past, at stars that might not exist anymore, at galaxies as they were before Earth formed, at a universe younger and smaller and stranger than it is today. And somewhere in that past, In a region of space so distant that it's almost meaningless to call it a place, there was a clustering of massive stars dying, creating bursts of energy, flashes of light that travelled through emptiness for 10 billion years, just to reach us, just to show up in our detectors as a pattern we don't quite understand. That's what we're looking at. That's what we're trying to make sense of. Not just a structure, not just a collection of gamma-ray bursts, but a signal from the deep past, a whisper from the early universe, a sign that something happened, something enormous, something we're only now beginning to see. And we don't know what it is. We might never know what it is. Not completely, but we're looking, we're thinking, we're trying to understand. And in that effort, in that reaching towards something beyond our grasp, there's something deeply human, a refusal to accept ignorance, a drive to explore, to question, to search for meaning in the vastness, even when the vastness doesn't cooperate, even when it presents us with mysteries too large to solve, even when it reminds us that we're small, temporary, limited creatures trying to comprehend something infinite. We keep looking anyway. We keep wondering. And perhaps that's enough. Perhaps the mystery itself is valuable, the not knowing, the sense of standing before something enormous and feeling both humbled and curious. Perhaps that feeling is what keeps us searching, what keeps us building better telescopes, developing better theories, asking better questions, because the universe doesn't owe us answers. It doesn't care if we understand it or not. It exists regardless of our comprehension. It follows its own laws. It unfolds according to processes that operated long before we existed and will continue long after we're gone. We're just observers, brief, curious observers, trying to make sense of patterns in the light. And sometimes those patterns point to something clear, something we can explain, something that fits neatly into our models. But sometimes they point to something else, something at the edge of our understanding, something that might be the largest structure in the universe, or might be nothing at all. And we're left with that uncertainty, that quiet, persistent not knowing, not as a failure, not as a disappointment, but as a reminder that the universe is still full of surprises, still capable of showing us things we didn't expect, still larger and stranger than we imagine. So we sit with it, this idea of something enormous lurking in the data, this pattern of gamma-ray bursts that defies our expectations, this structure that shouldn't exist but might. We turn it over in our minds. We examine it from different angles. We test our assumptions. We question our methods. And we accept that for now, we don't have a complete answer. That's uncomfortable for us. We like answers. We like understanding. We like being able to point at something and say, this is what it is. This is how it works. This is why it's here. But the universe doesn't always give us that satisfaction. Sometimes it gives us questions instead. Sometimes it shows us something so strange, so unexpected, that all we can do is stare and wonder. And perhaps there's wisdom in that wondering, in not rushing to conclusions, in not forcing an explanation where none quite fits, in allowing ourselves to sit with the mystery and let it be mysterious for a while. Because the truth is, we're still learning how to see. Our telescopes are new. Our understanding is young. We've only just begun to map the universe on these enormous scales. And already we're finding things that challenge us. Things that don't fit the patterns we expected. Things that force us to reconsider what we thought we knew. That's not a problem. That's progress. That's how science works. How understanding grows. Not through having all the answers, but through finding better questions. And this structure, whatever it is, has given us some very good questions. Questions about time and scale. About how large things can grow in a universe that's still quite young. about whether our models of structure formation are complete or missing something crucial. Questions about randomness and pattern, about how we distinguish between coincidence and causality on cosmic scales, about what it means for something to be real when we can only see its shadows. Questions about the limits of knowledge itself, about what we can and cannot understand with the tools we have, about whether some mysteries might remain mysteries, not because we're not clever enough, but because the universe is genuinely more complex than our frameworks can capture. These are not easy questions. They don't have quick answers, but they're important questions, the kind that push us forward, that make us think harder, that force us to be more careful, more rigorous, more humble in our claims. And in the meantime, the structure remains. Or doesn't remain. We're not sure. The gamma-ray bursts are still clustering in that region of the sky. The observations haven't changed. The pattern is still there. What's changed is our certainty about what it means. We've gone from thinking we understood cosmic structure formation to realizing there might be gaps in that understanding. From assuming we knew the limits of what could exist to questioning whether those limits are real. From having a clear picture of the universe to having a picture with a strange, uncertain smudge in one corner. And that smudge bothers us. Not because it's ugly, but because it doesn't fit. Because it suggests that the picture might be incomplete. That there might be other smudges we haven't noticed yet. That the universe might be weirder than the neat models we've built. But weird doesn't mean wrong. Weird just means unexpected, unfamiliar, outside our current framework, and unexpected things are often the most interesting. They're the things that teach us something new, that expand our understanding, that remind us we're not done learning. So we keep looking at this clustering of gamma-ray bursts. We keep measuring, keep analyzing, keep trying to work out what it means. Not because we're certain we'll find an answer, but because the looking itself is valuable. Because every observation tells us something about the universe, even if it's just that the universe is more complicated than we thought. Because in the act of trying to understand, we push our knowledge a little further. We develop better tools, we refine our methods, we learn what we don't know, and slowly over time the picture becomes clearer. Not all at once, not in a sudden revelation, but gradually, piece by piece, one observation at a time. Perhaps in 10 years, we'll have enough data to say definitively whether this structure is real or not. Perhaps we'll find other structures like it and realize it's part of a larger pattern we hadn't seen before. Perhaps we'll discover new physics that explains how something this large can form. Or perhaps we'll determine it was a statistical anomaly after all. An unlikely but not impossible arrangement of random events. We don't know yet. And that's all right, because this is how exploration works. You don't start with answers, you start with observations, with data, with things that don't quite make sense, and you work your way towards understanding slowly, carefully, with a willingness to be wrong, with an acceptance that some questions take decades to answer. The universe has been here for 14 billion years. It can wait a little longer for us to figure it out. In the meantime, we have this mystery, this enormous uncertain thing at the edge of our understanding, this structure that might be the largest object in the universe, or might be nothing but a pattern in the noise. Either way, it's beautiful. Beautiful in the way that all mysteries are beautiful, not because they're easy or comfortable, but because they remind us how much we have yet to learn. Because they show us that the universe is still capable of surprising us, still full of wonders we haven't imagined, still larger and stranger and more magnificent than we can fully comprehend. And we get to be here, watching it unfold, trying to understand it, trying to make sense of these signals from the deep past, trying to read the story written in patterns of light across billions of years of space and time. We might not understand it perfectly. We might never understand it perfectly, but we get to try. And in that trying, in that reaching towards understanding, we become more than we were, more aware, more curious, more connected to something vast. So we keep looking up, keep asking questions, keep wondering what's out there in the darkness between the stars. And sometimes, just sometimes, the darkness looks back, not with answers, not with explanations, but with mysteries, with things so large we can barely see them, so strange we can barely believe them, with reminders that the universe is not here to make sense to us. It's here to be what it is, vast, ancient, incomprehensible, and we're here to witness it, to observe it, to marvel at it, to not understand it, and to be okay with that. Because understanding isn't the only thing that matters. Wonder matters too. Curiosity matters. Humility matters. The willingness to stand before something enormous and simply let it be enormous. To see it without needing to explain it. To feel its scale without needing to reduce it to something manageable. That's what this structure gives us. This Hercules Corona Borealis Great Wall. This clustering of gamma-ray bursts. This mystery at the edge of everything we know. It gives us a chance to be small, to feel the weight of our own ignorance and find it not crushing, but liberating. To realize that we don't have to understand everything, that some things can remain unknown, and that's not a failure. It's just the way things are. The universe is under no obligation to make sense. It doesn't care about our models or our theories or our need for closure. It simply is, doing whatever it does, following whatever laws it follows, creating structures that might be too large to exist, or might not be structures at all, sending us signals we can detect but not interpret, showing us patterns we can measure but not explain. And we do our best. We build our telescopes, we gather our data, we run our calculations, we propose our theories and test them. We argue and debate, and slowly narrow down the possibilities, and eventually maybe we arrive at something like understanding. But even when we do, even when we think we've figured something out, the universe has a way of showing us we were wrong. Or not wrong exactly, but incomplete. That our understanding, however detailed, is still just a small sketch of something much larger. That's what this structure might be showing us now. That our sketch of how cosmic structures form is missing something. A detail we overlooked, a possibility we didn't consider, a piece of physics we don't know yet, or maybe not. Maybe our sketch is fine and this is just an outlier, an exception, a rare event that doesn't require us to redraw the whole picture. We don't know. And in that not knowing, there's a strange kind of peace. Because it reminds us that we're part of something larger than ourselves. Part of a process of discovery that's been going on for centuries and will continue long after we're gone. We're not expected to solve everything, to answer every question, to understand the entire universe in a single lifetime. We're just expected to look, to wonder, to add our small piece to the growing picture, and to pass it on to whoever comes next. So we sit here, in this moment, with our telescopes pointed at a region of the sky we can barely comprehend, watching signals from 10 billion years ago, trying to understand what they mean, knowing we might not figure it out, and being okay with that. Because the mystery is part of the beauty. The not knowing is part of the experience. The uncertainty is what makes it worth pursuing. If we understood everything, if the universe laid itself bare and explained all its secrets, what would be left to discover? What would be left to wonder about? What would keep us looking up at the stars with that same sense of awe we felt since the beginning? So perhaps it's good that we don't know what this structure is. Perhaps it's good that the universe still has the power to confuse us, to challenge us, to show us things we can't explain. Perhaps that's exactly what we need. Not answers, not certainty, but questions, mysteries, reminders that we're still at the beginning of this journey, and the journey is long, longer than any of us will live to see completed. But that's all right, because the journey itself is the point, the looking, the wondering, the slow accumulation of knowledge, the gradual expansion of what we understand, and the simultaneous realization of how much we don't. That's what this structure represents, not just a possible object in space, but a symbol of our limitations and our aspirations, of what we can see and what we cannot understand, of the gap between observation and comprehension and the effort required to bridge it. And that gap might never close completely. We might always be chasing understanding that stays just out of reach, but we'll keep chasing anyway, because that's what we do. That's what makes us human. This need to know, this drive to understand, this refusal to accept mystery as the final answer, even when mystery is all we have, even when the universe gives us nothing but questions, even when we stand before something 10 billion light years across and realize we have no idea what we're looking at. We keep looking anyway. We keep measuring, calculating, theorizing. We keep trying to make sense of the senseless, to find pattern in chaos, to understand the incomprehensible. And sometimes we succeed. Sometimes the universe reveals its secrets and we feel that rush of comprehension, that moment when everything clicks into place and suddenly the mystery dissolves and we see clearly what was obscured before. But not this time. Not yet. This time, the universe is keeping its secrets. This time, we're left with observations we can't quite explain, with data that doesn't quite fit, with a structure that shouldn't exist but might, and we're left to wonder, to sit with the uncertainty, to accept that for now we don't have answers, to be comfortable with not knowing, because this is where we live, in the space between what we can see and what we can understand, between the data and the theory, between the observation and the explanation, in that uncertain space where science happens, where questions outnumber answers, where mysteries pile up faster than we can solve them, where the universe keeps showing us new things to not understand, and we wouldn't have it any other way, because this is what we signed up for, this endless pursuit of understanding in a universe that's always one step ahead, this humbling recognition that we're small creatures with limited brains trying to comprehend something infinite, this acceptance that we might never know everything, but we'll keep trying anyway, because the trying is what matters, the looking, the wondering, the asking, the refusal to turn away just because something's hard to understand, the commitment to keep pushing at the edges of knowledge, even when those edges push back. So here we are, standing before the largest structure we've ever found, or maybe not a structure at all, looking at something we can measure but not explain, something that challenges everything we thought we knew about how the universe works. And we don't know what it is. We might never know what it is, but we're here. We're looking. We're trying. And that's enough, because this is how it feels to be human in an infinite universe. Small, curious, uncertain, seeing things we can't explain, measuring things we can't comprehend, living with mysteries we might never solve, and finding beauty in that, finding meaning in the search itself, not just the finding wonder in the not knowing. So we'll keep watching this region of the sky, keep collecting data on these gamma ray bursts, keep trying to work out what they mean, and maybe one day we'll understand. Maybe one day it'll all make sense, or maybe not. Maybe this will remain a mystery, a clustering of signals we can see but never quite explain, a a structure at the edge of possibility that reminds us how much we have yet to learn. Either way, it's there. The largest thing we've ever found, or the most elaborate coincidence, or something else entirely. We don't know, and that's where we'll leave it. In the uncertainty, in the mystery, in the vast unknown spaces between the stars, where the universe keeps its secrets, and we keep looking, where the universe keeps its secrets, and we keep looking. There's something worth considering about the act of looking itself, about what it means to point a telescope at the sky and collect light that's been travelling for billions of years. We think of it as observation, as gathering data, as seeing what's there. But it's more complicated than that, because what we see depends not just on what's there, but on how we look, what we're looking for, what we expect to find. When we map the sky, we're not creating a perfect representation of reality. We're creating a model, an interpretation, a translation of electromagnetic signals into something our minds can work with. And that translation involves choices about which wavelengths to observe, which patterns to emphasize, which signals to consider noise, and which to consider meaningful. These aren't arbitrary choices. They're based on physics, on statistics, on decades of accumulated knowledge. But they're still choices, and different choices might lead to different conclusions about what we're seeing. This structure, this clustering of gamma-ray bursts, emerged from one particular way of looking at the data. If we'd been looking for something else, we might not have noticed it. If we'd applied different statistical methods, we might have concluded it wasn't significant. If we'd observed different wavelengths, we might have seen a completely different pattern. That doesn't mean it's not real, but it does mean that reality and observation are not the same thing. That what we see is always filtered through the instruments we use and the frameworks we bring to the seeing. And this raises uncomfortable questions. Questions about how much of what we think we know is actually out there, and how much is in the way we're looking. Questions about whether other structures like this exist but we haven't noticed them because we haven't looked in the right way. Questions about what we might be missing simply because we don't know to look for it. These questions don't have easy answers. They sit at the boundary between science and philosophy, between the practical work of observation and the deeper problem of how we can know anything at all about a universe so vast and strange. And they matter. Because if this structure is real, if it's genuinely something that shouldn't exist according to our models, then we need to understand why our models failed. Was it because we were missing some crucial piece of physics? Or was it because we were looking at the data with assumptions that turned out to be wrong? Or was it something else entirely, some flaw in how we translate observation into understanding? We don't know, and the not knowing makes everything harder, because we can't just add a new piece to the puzzle. We have to question whether the puzzle itself is shaped the way we thought it was. There's a tendency in science to want problems to have clean solutions, to want mysteries to resolve into facts, to want the universe to eventually make sense if we just work hard enough at understanding it. And often that's what happens. Often mysteries do resolve. Observations that seemed impossible turn out to have perfectly reasonable explanations once we understand the context better. But not always. Sometimes observations remain stubbornly difficult to explain. Sometimes the universe presents us with things that don't fit any framework we have, and we're left to choose between changing the framework or questioning the observation. Neither choice is comfortable. Changing the framework is hard because frameworks are built on years of work, decades of experiments and observations and theoretical development. You don't overturn all of that lightly. You need very strong evidence, multiple independent confirmations, a clear path forward that explains not just the new observation, but everything else we already knew. But questioning the observation is hard too, because it means accepting that our instruments might be misleading us, that our methods might be flawed, that what seemed like a clear signal might just be noise arranged in a pattern that looks meaningful but isn't. And if that's true here, where else might it be true? What other observations might we need to question? So we're stuck between a structure that challenges our understanding and the possibility that there's no structure there at all, between expanding our physics and contracting our certainty, between the universe being stranger than we thought and our observations being less reliable than we hoped. And we work our way through this uncertainty slowly. We gather more data, we refine our methods, we test our assumptions, we look for other examples, other regions of the sky that show similar clustering, other patterns that might support or contradict what we're seeing here. We run simulations. We ask whether there's any combination of known physics that could produce something like this, any set of initial conditions that could lead to a structure this large. We examine our instruments, we check for systematic errors, we make sure we're not seeing an artifact of how we're processing the data, and gradually the picture becomes clearer. Not fully clear, not resolved, but clearer than it was. We learn which explanations definitely don't work, which possibilities we can rule out based on the evidence. We learn which questions we can answer and which ones we can't yet. We learn what we need to observe next. What measurements would help distinguish between the remaining possibilities? And the mystery shifts. It doesn't go away, but it becomes more specific, more focused, less a vague sense of something wrong, and more a precise question about a particular aspect of the universe we don't understand. That's progress. Not the dramatic kind, not the kind where everything suddenly makes sense, but the slow, patient kind. The kind that's built from years of work and thousands of small insights. The kind that characterizes most of science most of the time. Because despite what we sometimes imagine, science isn't usually about sudden breakthroughs. It's about gradual accumulation, steady refinement, the slow turning of uncertainty into knowledge. And that process takes time. More time than we'd like. More time than feels satisfying. But that's the nature of trying to understand something as complex as the universe. And this structure, whatever it is teaching us something about that process, about the gap between what we can observe and what we can explain, about how long it takes to move from seeing something to understanding it, about the patience required to sit with uncertainty while we work towards clarity, because we will work towards clarity. We won't just leave this as an unsolved mystery and move on. We'll keep at it, keep gathering data, keep testing hypotheses, not because we're guaranteed to succeed, but because that's what we do. There's something almost stubborn about it. This insistence on trying to understand even when understanding seems impossible. This refusal to accept mystery as a final answer, even when mystery is all we have. But maybe that stubbornness is necessary. Maybe it's what drives science forward. This unwillingness to give up. This commitment to keep pushing at the boundaries of knowledge even when those boundaries don't want to move. And sometimes they do move. Sometimes persistence pays off. Sometimes the mystery that seemed impenetrable turns out to have a solution after all, once we've gathered enough data or developed the right theoretical framework or simply thought about it long enough. We've seen it happen before. We've seen observations that seem to violate known physics turn out to be perfectly consistent with it once we understood the context better. We've seen structures that seemed impossible turn out to be rare but allowed. We've seen mysteries resolve. So maybe this one will too. Maybe in 10 years or 20 or 50, we'll look back on this clustering of gamma ray bursts and understand exactly what it means. Maybe we'll have a clear explanation for why it exists and how it formed, and whether it's really the largest structure in the universe or just an artifact of our observation method. Or maybe not. Maybe this will remain uncertain. A pattern in the data that we can measure but never quite explain. An observation that sits at the edge of what our theories can account for. A reminder that the universe is under no obligation to fit our frameworks. Either way, we'll have learned something about the universe, about our methods, about the limits of what we can know, and that learning, that gradual expansion of understanding, is worth something even if it doesn't come with definitive answers. Because the universe is vast, vastly larger than we can observe, vastly older than we can trace, vastly more complex than we can model, and we're trying to understand it with instruments that can only see certain wavelengths of light, with mathematics that can only approximate the physics, with brains that evolved to understand distances of meters and timescales of years. It's remarkable that we can understand anything at all, that we can look at light from billions of years ago and extract meaningful information from it, that we can map the distribution of galaxies across the observable universe, that we can model how structures form and test those models against reality. And when our models fail, when we encounter something that doesn't fit, that's not a disaster. That's an opportunity to refine our understanding, to discover new physics, to expand the boundaries of what we know, or at the very least, an opportunity to understand more clearly what we don't know, to map the edges of our ignorance with the same precision we map the edges of the observable universe. To be honest about uncertainty instead of pretending we understand more than we do. And there's value in that honesty, in admitting when we don't know something, in acknowledging the limits of our current understanding, in being comfortable with mystery as a temporary state rather than a failure. Because science is not about having all the answers, it's about asking the right questions, about developing methods to investigate those questions, about being willing to change our minds when the evidence demands it. And this structure is giving us good questions to work with, questions that will drive research for years, questions that will push us to develop better instruments and better theoretical frameworks, questions that will keep us looking up at the sky and wondering. So in a strange way, it doesn't matter whether this structure is real or not. It matters that we're asking about it, investigating it, taking it seriously enough to gather the data needed to resolve the uncertainty. Because that process of investigation is how we learn, how we expand our knowledge, how we push at the boundaries of what's possible. And sometimes the investigation reveals that what we thought we saw wasn't there, that the pattern was an artifact, that the structure was an illusion. And that's okay too, because we still learned something about our instruments, about our methods, about the dangers of seeing patterns where none exist. Human pattern recognition is a powerful tool. It's what allowed our ancestors to find food and avoid predators, to read social cues and navigate complex environments. But it's also a double-edged sword, because we're so good at finding patterns that we sometimes find them where they don't exist. We see faces in clouds, constellations in random arrangements of stars, meaning in coincidence. And when we're looking at cosmic data, when we're examining the distribution of gamma ray bursts across billions of light years, we have to be very careful about that tendency. We have to distinguish between patterns that reflect underlying physical structure and patterns that are just statistical noise. And that's hard, really hard, because the line between the two isn't always clear. Sometimes a pattern is real but weak. Sometimes it's strong but meaningless. Sometimes it's somewhere in between, representing something real but not what we think it represents. And we have tools to help us make these distinctions. Statistical tests, significance thresholds, methods for estimating how likely a pattern is to occur by chance. But these tools aren't perfect. They give us probabilities, not certainties. They help us quantify our confidence, but they don't eliminate the possibility of error. So when we look at this clustering of gamma-ray bursts and calculate that it's unlikely to be random, we're not saying it's definitely a structure. We're saying the pattern is strong enough that it warrants further investigation, that it's interesting enough to follow up on, that it might be telling us something important about the universe. But might is the operative word. Might, not definitely. Might, not certainly. Might with all the uncertainty that word implies. And we have to live with that uncertainty, have to make decisions about where to point our telescopes and how to spend our research funding based on incomplete information. Have to choose which mysteries to pursue and which to set aside, knowing that we might be making the wrong choice. Science, in practice, is full of these uncomfortable choices, these moments where we have to act without complete knowledge, where we have to trust our judgment and our methods even though we know they're imperfect, where we have to move forward despite uncertainty because waiting for certainty means never moving at all. And most of the time, that works out. Most of the time, our methods are good enough. Our judgment is sound enough. Our understanding is complete enough to make progress. But sometimes it doesn't work out. Sometimes we pursue a mystery that turns out to be nothing. Sometimes we overlook something important because it didn't seem significant at the time. Sometimes we're just wrong. And that's part of the process too. Being wrong. Making mistakes. Following dead ends. It's not a flaw in the system. It's an inevitable consequence of working at the edge of knowledge where everything is uncertain and nothing is guaranteed. The question is not whether we'll make mistakes. We will. The question is whether we can learn from them, whether we can adjust our methods and our thinking based on what we discover, whether we can remain humble enough to admit when we're wrong and flexible enough to change course. And generally, we can. Science has a built-in error correction mechanism, a process of peer review and replication and debate that gradually filters out mistakes and converges on truth. It's not perfect, it's not fast, but it works. Over time, over many observations and many researchers and many iterations, we get closer to understanding. But that process takes patience, takes a willingness to sit with uncertainty for as long as it takes to resolve it, takes faith that the process will work even when progress seems impossibly slow. And for this structure, the process is ongoing. The uncertainty is still there. The mystery is still unsolved. We're somewhere in the middle of the investigation, with years or decades of work ahead before we'll have a clear answer. And that's frustrating. We want to know now, want to understand immediately, want the universe to reveal its secrets on our timeline instead of its own. But that's not how it works. The universe operates on timescales we can barely comprehend. Structures form over billions of years. Light travels for billions of years. Processes unfold across distances so vast that our entire civilization is less than a blink. And we're trying to understand all of this in the span of a human lifetime, in the span of a career even, a research grant, a PhD thesis. We're trying to fit cosmic timescales into human ones, and it doesn't quite work. So we do what we can. We make our observations. We build our models. We publish our papers. We pass our work on to the next generation, who will build on what we've done and pass it on to the generation after that. And slowly, incrementally, understanding grows. Not in any one person's lifetime, not in any one research project, but across the collective effort of thousands of researchers over decades and centuries. That's how we come to understand things on cosmic scales. Through patience, through collaboration, through the slow accumulation of knowledge across generations. And this structure will be part of that process, part of the ongoing conversation about how the universe works and what it contains. Part of the long thread of inquiry that connects ancient astronomers looking up at the stars, to future researchers with instruments we can't imagine studying questions we haven't thought to ask yet. And somewhere in that thread, this mystery will resolve. Or it won't. But either way, the asking will have mattered. The investigation will have taught us something. The uncertainty will have pushed us to be more careful, more rigorous, more honest about the limits of our knowledge. Because that's what good mysteries do. They make us better, more thoughtful, more humble. They remind us that we don't know everything, that the universe is full of surprises, that confidence should be proportional to evidence, not desire. And they keep us curious, keep us looking up at the sky and wondering what's out there, keep us building telescopes and writing papers and arguing with colleagues about what the data means. Keep us engaged in this long, slow process of trying to understand something vastly larger than ourselves. And maybe that engagement is the point. Maybe the value isn't in the answers, but in the asking. In the way that trying to understand the universe changes us, makes us think differently, expands our sense of what's possible. Because when you spend your days thinking about structures 10 billion light years across, it changes your perspective. It makes human concerns seem smaller, not unimportant, but contextualized against something vast. It reminds you that the universe was here long before we arrived and will continue long after we're gone, that our understanding, however sophisticated, is still just a tiny scratch on the surface of something incomprehensibly deep. And there's something grounding about that, about being reminded of our place in the cosmic order, about feeling small, not in a crushing way, but in a liberating one. Because if we're small, then our mistakes are small too. Our errors are not cosmic catastrophes, but temporary setbacks in an ongoing process. Our misunderstandings are not failures, but opportunities to learn. Our uncertainties are not weaknesses, but honest acknowledgements of the limits we're working within. And we can be okay with that. Can accept that we're doing the best we can with the tools we have. That we're part of a larger effort that transcends any individual contribution. That our small piece of the puzzle matters even if we never see the completed picture. So we keep going, keep observing this region of the sky, keep analyzing the data, keep refining our understanding of what we're seeing and what it might mean, not because we're certain we'll succeed, but because the effort itself is worthwhile, because trying to understand is better than not trying, because curiosity is its own justification, and slowly, over months and years and decades, the picture will sharpen. New observations will come in, new telescopes will launch, new theoretical frameworks will be developed, and we'll understand more. Not everything, perhaps not even most things, but more than we do now. And that's enough. That incremental progress, that gradual expansion of knowledge, that slow push against the boundaries of what we can understand. That's what we're here for. So we sit with this mystery a little longer, this structure that might be the largest thing in the universe, this clustering of signals from the deep past, this pattern that challenges our understanding and resists easy explanation. We sit with it and we work on it, and we accept that we might not solve it today or tomorrow or even in our lifetimes. But we trust that the process will continue, that others will pick up where we leave off. That understanding will come eventually, even if we're not there to see it. And in the meantime, we have the wonder, the awe of looking at something so vast and strange, the curiosity of not knowing what it is, the humility of confronting the limits of our understanding. And that's not nothing. That's something profound. Something that connects us to every human who's ever looked up at the sky and wondered. Every ancient astronomer tracking the movements of planets. Every early scientist realizing the Earth wasn't the center of the universe. Every modern researcher pushing at the edges of what we can observe and understand. We're all part of the same project, the same long, slow effort to make sense of this strange and beautiful universe we find ourselves in. And this structure, whatever it turns out to be, is part of that story, part of the ongoing narrative of human curiosity confronting cosmic mystery. So we let it be mysterious for now. We accept the uncertainty, embrace the not knowing, and we keep looking anyway, and we keep looking anyway. There's a history to this kind of looking that stretches back further than we might think. Long before we had telescopes powerful enough to detect gamma-ray bursts from billions of light years away, we were finding things in the sky that didn't make sense. Things that challenged the prevailing understanding of how the universe worked. In the early 20th century, astronomers noticed something strange about certain fuzzy patches in the sky. They called them nebulae, clouds of gas, they thought, within our own galaxy. But when they measured the light from these nebulae more carefully, they found something unexpected. The light was shifted, stretched towards the red end of the spectrum in a way that suggested these objects were moving away from us. Faster than anything within our galaxy should be moving, and that observation didn't fit. It didn't make sense within the framework they had, so they had to choose. Either their observations were wrong somehow, or their framework was incomplete. They chose to trust the observations, and that choice led to one of the most profound realizations in the history of science. Those nebulae weren't clouds of gas within our galaxy. They were galaxies themselves, entire systems of billions of stars, far beyond the bounds of the Milky Way. And the universe was vastly larger than anyone had imagined. That shift in understanding didn't happen overnight. It took years of observation, years of debate, years of slowly accepting that the universe was stranger and larger than the models predicted. And even then, there was resistance. Because changing your fundamental picture of reality is hard. It requires letting go of certainties you've built your understanding on. It requires admitting that what seemed obviously true might not be. But the observations kept coming. More galaxies, more measurements, more evidence that the universe extended far beyond what anyone had thought possible. And gradually the framework shifted to accommodate this new reality. We're in a similar position now with this structure. We have observations that don't fit comfortably within our current framework. A clustering of gamma-ray bursts that seems to suggest a structure too large to exist, and we're faced with the same choice. Trust the observations and question the framework, or question the observations and keep the framework intact. Neither path is comfortable. But we've been here before. We've encountered cosmic mysteries that seemed impossible to resolve, and sometimes resolving them required expanding our understanding in ways we didn't anticipate. The expansion of the universe itself was one of those mysteries. When astronomers first noticed that distant galaxies were moving away from us, it seemed to violate basic physics. If everything was moving away from a single point, didn't that make us special? Didn't that put us at the center of the universe? But no, the mathematics showed something stranger. Space itself was expanding. Every point was moving away from every other point. There was no center, no special location, just a universe that was larger today than it was yesterday and would be larger tomorrow than it is today. That realization required a fundamental shift in how we thought about space. It wasn't a fixed stage on which events occurred. It was dynamic, changing, stretching, and that stretching had implications for everything, for how we understood time, gravity, the history of the universe, the future of everything. But accepting that required giving up old certainties about the nature of space, about the stability of the cosmos, about our ability to trust our intuitions about how reality should work. And we did it. We gave up those certainties because the evidence demanded it, because the observations were too consistent, too reproducible, too clear to ignore. But it took time, decades of observations, multiple independent confirmations, theoretical work to show how the expansion fit with other aspects of physics. It wasn't a single eureka moment. It was a slow, collective process of coming to terms with something profoundly counterintuitive. And maybe that's where we are now with this structure. At the beginning of a similar process, confronting observations that don't fit, trying to work out whether they're telling us something profound about the universe or revealing limitations in our methods. Sitting with uncertainty while we gather more data and develop better theories. The difference is we're aware of the process now in a way earlier astronomers weren't. We know that cosmic mysteries don't usually resolve quickly. We know that observations can be misleading, that patterns can be artifacts, that what seems significant might turn out to be noise. But we also know that sometimes observations that seem impossible are pointing to something real, something that requires us to expand our understanding so we hold both possibilities in mind. This could be a genuine structure that challenges our models of cosmic evolution. Or it could be a statistical fluctuation that looks meaningful but isn't. We don't know yet which it is. And that's different from earlier cosmic mysteries in an important way. We're more uncertain now, more cautious, more aware of the ways our observations can mislead us. We're less likely to jump to conclusions, less likely to claim we've discovered something revolutionary before we've thoroughly checked for other explanations. That caution is good. It protects us from embarrassing mistakes, from claiming discoveries that don't hold up under scrutiny, but it also means we sit with uncertainty longer. We're slower to commit to an explanation, slower to update our frameworks. We require more evidence, more confirmations, more cross-checks before we're willing to say we've found something real. And for a structure like this, that means years or decades of uncertainty. Years of not knowing whether what we're seeing is real or illusory. Years of gathering data, running analyses, debating interpretations. Years of living with the question rather than the answer. For some people, that's frustrating. They want to know now, want a definitive answer, want the mystery solved so we can move on to the next one. But that's not how cosmic mysteries work. They unfold on their own timescale, not ours. They resolve when we have enough evidence, not when we want an answer. And sometimes they don't resolve at all. Sometimes we gather all the data we can and we're still left with ambiguity, still uncertain about what we're looking at, still unable to distinguish between competing explanations. That's uncomfortable. It feels like failure, like we should be able to figure this out if we just work hard enough. But maybe it's not failure, maybe it's just honesty. An honest acknowledgement that some questions are harder than others, that some observations sit right at the edge of what we can reliably detect and interpret, that the universe doesn't always give us clean answers. And there's a maturity in accepting that, in being comfortable saying we don't know instead of forcing a conclusion that isn't justified by the evidence, in living with uncertainty rather than replacing it with false certainty, because false certainty is dangerous. It stops us from looking further, from questioning our assumptions, from remaining open to new evidence. It creates the illusion of understanding where none exists. So maybe it's better to say we don't know. To admit that this clustering of gamma-ray bursts is genuinely puzzling, that it might be the largest structure in the universe, or it might be nothing, and we can't say for certain which. To accept that ambiguity as the current state of our understanding and keep working to resolve it. That's harder than claiming we've figured it out. Harder than declaring this definitively a structure, or definitively not. But it's more honest, more true to what the evidence actually shows, and honesty matters in science. It's what distinguishes it from other ways of knowing. The commitment to following the evidence wherever it leads, even when it leads to uncertainty. The willingness to admit ignorance rather than pretending to knowledge we don't have. So we say it clearly. We don't know what this is. We have observations, we have hypotheses, we have ongoing investigations, but we don't have a definitive answer, and we're okay with that. Not happy about it, perhaps, not satisfied, but okay with it as a temporary state, as the current position on a longer journey towards understanding. Because the journey continues, every year our instruments get better, our methods more refined, our theoretical frameworks more sophisticated. Every year we're able to see fainter objects, detect subtler patterns, distinguish signal from noise more reliably. And that progress will eventually help us understand this structure, or help us understand that there is no structure. Either way, we'll know more than we do now. But that knowing will come slowly. Not in a sudden flash of insight, but in a gradual accumulation of evidence. One observation at a time, one analysis at a time, one paper at a time, building towards a picture that's clearer, more complete, more certain. And in the meantime, we live with the mystery. We teach it to students. We write papers about it. We debate it at conferences. We incorporate it into our understanding of what we know and what we don't. We use it as an example when we talk about the limits of current cosmology, and it becomes part of the landscape of our knowledge. Not a solved problem, not a definitively answered question, but an ongoing investigation, a work in progress, a mystery we're actively working to understand. And that's fine. That's normal, actually. Science is full of these ongoing investigations, these partially understood phenomena, these questions we're in the process of answering but haven't answered yet. They don't make headlines the way discoveries do. They don't generate the same excitement as a clear finding or a revolutionary new theory. But they're where most of the work happens. In the patient, careful investigation of things we don't fully understand. In the slow process of gathering evidence and testing hypotheses and ruling out alternatives. In the unglamorous but essential work of trying to figure out what's actually going on. And for this structure, that work continues. Researchers are still analysing the data, still looking for additional gamma-ray bursts in this region, still trying to map the distribution of galaxies to see if there's a corresponding concentration of matter. They're comparing different statistical methods, testing for systematic errors, checking whether the clustering is robust to different ways of analysing the data. They're running simulations, trying to see if there's any way to form a structure this large within the time available, exploring whether different assumptions about initial conditions or dark matter properties might make it possible. All of this takes time, years of effort by dozens of researchers across multiple institutions. Careful, meticulous work that rarely makes news but slowly advances our understanding, and eventually that work will bear fruit. We'll have a clearer picture of what we're looking at. We'll be able to say with more confidence whether this clustering is real or coincidental, whether it requires new physics or fits within what we already know. But we're not there yet. We're still in the messy middle of the investigation, still working through the uncertainty, still trying to figure out what the observations are telling us, and that's where we'll be for a while longer. Not because we're not working hard enough, but because this is genuinely difficult, because cosmic scale structures are hard to study, because the signals are subtle and the noise is significant and distinguishing between them takes time. So we keep at it, keep gathering data, keep refining analyses, keep pushing towards understanding, knowing that it might take years to get there, knowing that we might never get complete certainty, but doing it anyway because it matters, because understanding the universe matters, because knowing what's out there, even when what's out there is strange and puzzling, is worth the effort. And along the way, we learn things we didn't expect to learn, things about our instruments, things about our methods, Things about the universe that we wouldn't have discovered if we weren't investigating this mystery, because that's how science works. You start investigating one question and you end up learning about 10 others. You develop a new technique to study one problem and it becomes useful for studying something completely different. You follow one mystery and it leads you to others you didn't know existed. So even if this structure turns out to be nothing, even if the clustering is just a statistical fluctuation, the investigation won't have been wasted. We'll have learned something, refined something, advanced our capabilities in some way. And if it does turn out to be real, if it is a genuine structure that challenges our understanding, then we'll have learned something even more valuable. We'll have discovered that the universe is stranger than we thought, that our models need updating, that there's more to understand. Either outcome moves us forward. Either way, we know more at the end than we did at the beginning, and that's the point of all this. Not to confirm what we already believe, but to discover what we don't yet know, to push at the boundaries, to find the places where our understanding breaks down and needs to be expanded. This structure, real or not, is one of those places, a boundary, an edge, a point where what we think we know meets what the universe is actually showing us, and the two don't quite match. And that mismatch is valuable. It's where progress happens, where new understanding emerges, where science advances. So we sit with it, this uncomfortable mismatch between theory and observation, this tension between what should be and what appears to be, this uncertainty about whether we're seeing something profound or something mundane. We sit with it and we work on it, and we trust that eventually the tension will resolve, not on our timeline, not according to our preferences, but on its own terms, in its own time. And we accept that. Accept that cosmic mysteries don't care about our need for closure. Accept that understanding comes when it comes, not when we want it. Accept that our role is to do the work, gather the evidence, follow the process, and let the answers emerge at their own pace. Because that's what it means to study the universe. To engage with something vastly larger and older and stranger than ourselves. To accept that it won't conform to our expectations or our timelines. To do the work anyway because the work itself is meaningful. And this work, this investigation of a possible structure at the edge of the observable universe, is meaningful. Not because it will definitely lead to a revolutionary discovery, but because it represents our best effort to understand something genuinely puzzling. Because it shows us taking observations seriously even when they're uncomfortable. Because it demonstrates the process of science at its most honest. We see something we don't understand. We investigate it carefully. We resist the urge to jump to conclusions. We gather evidence. We test hypotheses. We remain uncertain until the evidence justifies certainty. And sometimes that takes a long time. Sometimes it takes longer than we'd like. But we do it anyway, because it's the right way to do science. The only way, really, when you're dealing with questions this large and evidence this subtle. So the investigation continues, slowly, carefully, patiently, with all the uncertainty that entails, with all the discomfort of not knowing, with all the humility required to admit that we're working at the very edge of what we can observe and understand. And somewhere in that work, in that patient investigation, we find meaning. Not in having all the answers, but in the asking itself, in the effort to understand, in the willingness to confront mystery and uncertainty and not turn away, because that's what makes us human, not our certainty, not our knowledge, but our curiosity, our drive to understand even when understanding seems impossible. And this structure, whatever it is, calls to that drive, challenges us, puzzles us, refuses to be easily explained. And in doing so, it keeps us looking, keeps us wondering, keeps us engaged with this vast and strange universe we find ourselves in, and maybe that's enough. Maybe the mystery itself, the not knowing, the ongoing investigation, is as valuable as any answer we might eventually find, because it keeps us humble, keeps us curious, keeps us aware that the universe is larger and stranger than we imagine, and we need that reminder. Need to be reminded that we don't have everything figured out, that there are still mysteries worth investigating, that the universe still has the power to surprise us. So we let this structure remain mysterious for now. Let it sit in that uncertain space between observation and explanation. Let it challenge us and puzzle us and refuse to fit neatly into our frameworks. And we keep looking at it, keep studying it, keep working towards understanding, even if that understanding is years away, even if it never comes completely, because this is what we do. This is who we are, curious creatures on a small planet, looking out at an incomprehensibly vast universe and trying to make sense of what we see, sometimes succeeding, sometimes failing, but always looking, always wondering, always reaching towards understanding, even when it stays just beyond our grasp. And in that reaching, in that effort, we find something worthwhile. Not certainty, not complete knowledge, but connection to something larger, to the process of discovery that's been going on for centuries and will continue long after we're gone. We're part of that process now, part of the long line of humans who've looked up at the sky and wondered what they were seeing. Part of the collective effort to understand the cosmos, adding our small contribution to a project that transcends any individual life. And this structure is part of that contribution, part of what we're handing down to future generations, a mystery we're working on, an observation we're trying to understand, a question we're in the process of answering, and they'll pick up where we leave off. They'll have better instruments, better methods, better theories. They'll see things we can't see, understand things we can't understand, and they'll move the investigation forward, but they'll still be dealing with uncertainty, still confronting mysteries, still working at the edge of what's known, because that edge keeps moving. As we understand more, we encounter new things we don't understand. The frontier of knowledge expands, but it never disappears. So there will always be mysteries, always things we're trying to understand but haven't figured out yet, always observations that don't quite fit our frameworks, and that's not a failure of science. That's science working as it should, confronting what it doesn't understand, investigating carefully, following evidence wherever it leads. And this structure is one of those mysteries, one of the things we don't yet understand but are actively working to figure out. One of the edges of our current knowledge where observation and theory don't quite match, and we're trying to understand why. And we'll keep working on it for as long as it takes, with all the patience and care and rigor that cosmic mysteries require, until eventually, one way or another, we understand it better than we do now. And then we'll move on to the next mystery, the next observation that doesn't fit, the next challenge to our understanding, because they're always there, always waiting, always calling us to look deeper, think harder, understand more. And we'll answer that call, because that's what we do. That's what it means to be curious, to be human, to look up at a vast and mysterious universe and refuse to accept mystery as the final answer, even knowing we might never have all the answers, even knowing that some mysteries might remain mysteries forever. We look anyway, we wonder anyway, we reach for understanding anyway, because in that reaching we find who we are, small, curious, persistent, standing before something incomprehensibly large and choosing to try to understand it anyway. And this structure, this possible largest object in the universe, represents that choice, that decision to investigate even when success isn't guaranteed. to gather evidence even when interpretation is difficult, to sit with uncertainty even when certainty would be more comfortable. It represents science at its best and most honest, acknowledging what we don't know, working to expand what we do know, accepting that the process takes time and the outcome isn't guaranteed. And in that honesty, in that patient work, there's something beautiful. Not the beauty of definitive answers, but the beauty of genuine inquiry, of minds turned towards questions that matter, of effort devoted to understanding something vast and strange. And we get to be part of that, get to contribute our small piece to the larger puzzle, get to look at this clustering of gamma ray bursts and wonder what it means, get to investigate and analyze and slowly, carefully work towards understanding. And that's a privilege, a profound privilege, to live in a time when we can observe the deep universe, when we can detect signals from billions of years ago, when we can ask questions about the largest structures in existence and actually have the tools to investigate them. So we use those tools, we ask those questions, we do that investigation, and we accept that the answers might not come quickly, that understanding might take years or decades, that we might be handing this mystery on to future generations still partially unsolved. And that's all right. That's how it should be. Because the universe is vast and we are small, and understanding takes time. So we give it that time. We do the work without rushing. We gather the evidence carefully. We think deeply about what it might mean, and we live with not knowing, with uncertainty as a companion rather than an enemy, with mystery as a feature of the universe, not a flaw in our understanding. Because maybe mystery is what makes it all worth doing, what keeps us curious, what drives us forward, what reminds us that there's always more to discover, always more to understand, always more wonder waiting just beyond the edge of what we know. And this structure, whatever it turns out to be, is part of that wonder, part of the vast, strange, beautiful universe we're privileged to observe, part of the ongoing story of human curiosity confronting cosmic mystery. And we're grateful for it, grateful for the challenge, grateful for the mystery, grateful for the opportunity to wonder, because in the end, that wondering might be the most human thing we do, that reaching towards understanding even when it stays beyond our grasp, that refusal to stop looking just because something's hard to see, that commitment to asking questions even when the answers don't come easily. So we keep asking, keep looking, keep wondering what this thing is that we've found at the edge of everything, and we accept that we might not know, not today, not tomorrow, maybe not ever, but we look anyway. And in that looking we find something worth having, not answers, but wonder. And perhaps that's been the point all along,